answer this question, let me go back in time. When I was graduating student in the theoretical chemistry at the University of Santiago de Compostela, Spain, I met a brilliant professor called Dr. Julio Casado, who taught me lots of things, especially quantum chemistry. But life decided that I should work in artificial intelligence. And this is what I am doing since 1988. Then, some 10 years ago, I read a paper on quantum computing and say, hey, unbelievable, I understand it. And as a professor in the Faculty of Computer Science, I understood that our graduate students should know something about it. And I had a meeting with my dean in which I proposed a course on principles of quantum computing, but he said no because for him, quantum computing was more a guess than a fact. But I took this no as a yes, and I began to prepare by my own and for free a series of seminars on quantum computing that are now in the web page of the faculty. And as a result of this, my students are now familiar with the basic aspects of quantum computing, and I have the classroom full of students. Concerning the second part of your question, my participation in NASC is mainly due to my interest in practical applications of quantum computing and in the way Atos presented the project. A use case-oriented project, it was something encouraging to me. Then I contacted with Dr. Andrés Gómez from CESGA, which is a very important technological center in Santiago de Compostela. I presented my use case, and my use case was considered as potentially relevant. Atos included my use case in the proposal, and the proposal was funded by the European Union. And this is all the story. Well, let me put your question in context. Medical informatics has fast evolved in the past 3 decades, but the original ambition of being capable of constructing systems that cover the whole of medicine have not been realized yet. Rather, we still see a wide variety of handy applications covering selected disciplines. At the same time, we face a big data reality where clinical details have expanded due to technological advances. These developments lead to the reintroduction of highly specialized centers for computing and for data interpretations. And the thing is that we have to translate vast amounts of information into knowledge. The scope is enlarged to astronomical proportions, but the promise is still the same as it was in the 90s. In this respect, we have to take into account that computers can store huge amounts of medical data. We can use computers in many applications, such as medical imaging or clinical decision systems. And definitely the computer technology has revolutionized the field of medicine. Also, medicine is a perfect field to investigate new approaches of computer science in general and in artificial intelligence in particular. This is due mainly because medical knowledge is basically heuristic, medical knowledge is intrinsically symbolic, medical knowledge is uncertain by nature, and medical decisions are often based on trial and error approaches. This together implies that the role of computers in medicine has changed from simply faster and accurate monitoring systems to expert programs that are capable of enhancing the real skills of the physicians by means of the construction of a second opinion. But to be able to accomplish the task, we have to build a model of expert knowledge that emulates the actual behavior of the real expert. That means building a computational model of intelligent behavior in the target domain. In other words, we have to follow the protocols that the real expert follows when faced with a clinical case. Let me put you an example. In the field of oncology, we have to model a sequence of tasks. For example, evaluation of symptoms that may support the hypothesis that the patient could have breast cancer, performing an anamnesis and screening, acquisition of additional information that could help to confirm or discard the hypothesis, and if the hypothesis is confirmed, then we have to perform the staging of the breast cancer. Once we have the stage of the breast cancer, we have to prescribe the therapy, but finally, it is mandatory the follow-up of the evolution of the patient. However, this is a very time-consuming task in both design and execution phases. This is why we are paying great attention to the new technologies, such as quantum computing, in order to verify whether or not they can improve the performance of clinical approaches. Well, let me tell you that since 1956, I believe so, more or less, artificial intelligence is a hot topic, but even now it has a long way to go. It is true that there are already many applications in the field of medicine, and since the pioneering work of Sharif al-Buchanan by developing the expert system IC in 1975, lots of developments have been successful. We also find artificial intelligence in applications in cervical cancer diagnosis, skin cancer diagnosis, or even in the detection and treatment of certain breast cancers. My experience in the field is related with the weaning of patients from mechanical ventilation, intelligent system for management of patients in the intensive care units, also diagnosis and prognosis of the fetal state, intelligent interpretation of sleep apneas, and so on. But building an expert intelligent systems in oncology or in other knowledge domains is a difficult task that needs a well-established methodology that even now does not exist. Modeling expert knowledge is the goal of what we call knowledge engineering. And knowledge engineering is a discipline that is part of the artificial intelligence and whose purpose is the design and development of expert systems. This should be supported by methodologies trying to achieve a computer representation of the human knowledge and of the human reasoning. The work of knowledge engineers consists of extracting the knowledge of human experts and encoding said knowledge so that it can be processed by a system, by a program. The problem is that the knowledge engineer is not an expert in the field to be modeled, and the expert in the subject has no experience modeling his own knowledge in a way that it can be represented in a computer program. Since the task of acquiring knowledge is a difficult task, several stages have been identified to approach this work in a more systematic way. For example, we have the identification of the problem, where basic concepts are learned, the conceptualization, where the whole process is organized, the formalization, where the concepts and particular processes are analyzed, the implementation, where we convert the acquired knowledge in software, and finally, testing, where we analyze the performance of our intelligence system. And this means to be able to construct an entire methodology. Well, leaving apart the nuclear problem of the knowledge engineering task, one of the we could say also the major drawbacks of intelligent systems especially those that work in medical domains, is the appropriate handling of the inaccurate knowledge. We find concepts like uncertainty, imprecision, subjective probability, credibility, inconsistency of knowledge, plausibility, fuzzy concepts, etc. And there are many models that have been built to deal with inaccurate knowledge. The problem is that each model produces different results. The interpretation of this could be that knowledge is not deterministic. Moreover, inaccuracy appears spontaneously even if we use strict categorical models of reasoning. This could also be related with the concept of the entropy of the information. For these reasons, we are now investigating approaches based in quantum computing, since quantum computing is non-deterministic by nature, and since inaccuracy is an intrinsic property of quantum systems. Let me talk a little bit about that. In classical computing, the information unit is the classical bit, which can take only two values, 0 or 1. Something is false, something is true. But in quantum computing, the information unit is the quantum bit, which is a vector, which is a column vector that can also take two values. But the interesting thing is that quantum systems can be simultaneously in both states, unless we measure the qubit. This is called superposition. But when we measure the qubit, they collapse to conventional bits, but with a given probability. And this is a key point in the non-subjective treatment of inaccuracy. Well, we have several goals to complete, but perhaps the most important one is to find an efficient method to translate classical knowledge-based systems into quantum rule-based systems. With this approach, we try to take advantage of all the characteristics and properties that make quantum computing a better tool than classical computing to perform calculations. And that's all the story. Thank you very much.